Hello everyone, my name is Kosuke Handa from Fujita Corporation in Japan. Today I'd like to report several test results regarding expansive additive. The title of my presentation is here, Basic Properties of Cement Paste Mixed with Calcium Hydroxide Ethylene Composite Type Expansive Additive. In order to reduce drying shrinkage cracks on RC slab or buildings such as distribution center or warehouse in Japan, expansive additive is generally used. However, the mechanism how macroscopic expansion is given to cement paste has not cleared. To solve the problem, we try to elucidate the mechanism and make a hydration model of expansive additive. And this time, we conducted a basic experiment on cement paste mixed with the expansive additive to grasp physical and chemical property. Here is an example of a structure of a distribution center. We need to design of preventing drying shrinkage cracks. Expansive additive reacts at a very early age, and concrete expands during the condition changes from plastic to solid. After curing, slab concrete dries and shrinks. Expansive additives are roughly divided into lime-based type and CSA type. And in addition, there are two types of typical CSA type expansive additive. One is composed of free lime, anhydrous gypsums, and ilmenite, and the other is composed of minerals such as C3A and C4AF instead of ilmenite. This study deals with CSA type expansive additive including C3A and C4AF. From here, I will explain the experimental plan and the experimental results. The contents of the experiment is shown here. Here is the mixed proportion plan. The main parameter of the experiment was the replacement ratio of the expansive additive with cement, and which is from 2.6% to 12.9%. The water binder ratio is over 45%. Here is the mineral composition of Portland cement, and this cement includes 36% of C2S, and this is a mineral composition of expansive additive. And here are the measurement results of the particle size distribution of cement and expansive additive. The expansive additive is characterized by containing many particles with a larger particle size than cement. Next, setting time is explained. The setting time test was performed by modifying the standard test. The basic test method is GSR 5201, which is Japanese standard, and which is a big cat needle test that is almost the same as the ASTM C191 test. Normal consistency was not adopted in this study. The penetration depth of each paste was measured as it was. The test results are shown here. The setting time tended to be faster until the replacement ratio reached 6.4%. However, when it exceeded 6.4%, the setting time tended to delay gradually. Next, the expansion strain is explained. And expansion strain was measured using a test specimen of 50 mm times 400 mm and 10 mm thickness. Here is a photo of the measuring facility. The cement paste was casted into a polyester film to reduce friction from the formwork. The bottom plate was copper plate, and a Teflon sheet was installed between the bottom plate and the polyester film. In order to prevent the test piece specimen from drying, a polyester film was set on the upper surface after the paste was casted, and the specimen was covered with a wet cloth. And here is the relationship between the measurement results at 7 days of age and the expansive additive replacement ratio. Expansion strain showed a tendency to cause rapid expansion when the replacement ratio exceeded 6.4%. And next is compressive strength. Here is the strength ratio to the strength of the reference. The strength was higher when the expansive additives was mixed up to the replacement ratio of 6.4%, but the strength decreased when it exceeded 6.4%. And here. Next, observation results by microCT scanning will be explained. CT scanning was performed using Phoenix Nanotone M. The paste is casted into a resin bottle and cured at room temperature. At 3 days of age, the test piece was processed into a 1 mm square bar and measured. And here is a photo at the measurement. Here is a cross-sectional image of CT scanning. The image on the left is a replacement ratio of 8.4% and the right side is 10.6%. In both cases, cracks were generated radially from the particle surface of the expansive additive. In addition, the radial cracks tended to be longer when the replacement ratio was 10.6% than when it was 8.4%. From this result, we think that the expansion of the cement paste caused by the mixing of the expansive additive is caused by the growth of the expansive additive particle itself. Finally, observation and elemental analysis by Eason were explained. On the 3 days of age, the sample was crushed with a hammer to a size of about 5 to 10 mm, and hydration was stopped with liquid nitrogen. 1 month later, the sample was impregnated with epoxy resin under performing vacuum deforming, and cured. Phillips X30 Eason was used for testing. And this is a backscattered electron image of the expansive low particle. The main mineral is free lime, and this is free lime, and the gap between free lime is filled with a mixture of C3A, C4AF, and anhydrous gypsum. Also, here are an image of the expansive additive particles after hydration. The left side is a replacement ratio of 5.1%, and the center is 10.3%, and the right side is an enlarged photograph around C3A with a replacement ratio of 10.3%. From the result of the replacement ratio of 5.1%, ethylene was not generated inside the expansive additive, and only calcium hydroxide and monosulfate were generated. From the result of 10.3%, it was confirmed that monosulfate was present on the surface of C3A inside the expansive additive, and the ethylene was formed vertically from above. In addition, a large amount of pores were simultaneously generated around the ethylene. From these results, it is considered that when the replacement ratio exceeds 6.4%, ethylene is generated inside the expansive additive, and as a result, a rapid expansion strain is applied to the cement paste, resulting in a decrease in strength. The conclusions will be explained. Regarding a strain, the expansion strain increases sharply when the replacement ratio of expansive additive exceeds from 6.4%, and the setting time tended to be faster when the replacement ratio was up to 6.4%, but when the replacement ratio exceeded 6.4%, the setting time became slower as the replacement ratio increased. Compressive strength tended to decrease compared to reference when the replacement ratio exceeded 6.4%. And from the cross-section image of a replacement ratio 10.3% hardened cement paste bar obtained by CT scanning, microcracks are radially generated from the aggregated portion of the hydration product. This result shows that the strength decreasing is caused by the expansion of the EA particles themselves. From the image of the formation location of ethylene in expansive additive particle of a replacement ratio 10.3% paste, monosulfate exists on the surface of the C3A, and the needle-like ettringite grows vertically from above. In addition, a large quantity of pores was simultaneously formed around the ettringite. This result shows that the rapid strain expansion occurring near replacement ratio exceeding 6.4% is caused by this particle generated ettringite with pores. And as with delayed ettringite formation, we have concluded that the anhydrate of expansive additive dissolves in water once, and ettringite can be produced only when the sulfate ion concentration exceeds a certain threshold. Thank you very much for your attention.